I think the last thing to discuss, yes, just very briefly, look at that. Only a 15 or so minute lecture. You've probably heard carbon dioxide is a greenhouse gas, so I want to spend some time talking about that. There's other things besides carbon dioxide as greenhouse gases. And as it turns out, it's all about the bonds, okay? So when you have something that has a polar bond, so what makes a greenhouse molecule? Well, it needs to have actually not only just a polar bond, but overall the molecule needs to possess a dipole moment, okay? And the reason for that, I'll show you that in a moment. It's fairly complicated, but it has to do with how the molecule interacts with infrared radiation, okay? So I'm only going to describe the greenhouse effect here very, very briefly. I would encourage you to research more if that's interesting to you or if you're not familiar with it. But as visible light comes down to planet Earth from the sun, a huge amount of visible light, okay? It heats up the surface, and as a result, the surface gives off some of that heat. And it gives off some of that heat in the form of infrared radiation, okay? Just like actually I give off heat in the form of infrared radiation, okay? If we were to turn all of these lights off and you had some really fancy like spy tech infrared, night vision goggles or whatever, you would see me glowing infrared. Well, as it turns out, planet Earth also glows infrared because it's a fairly warm object in the grand scheme of things. Average planet-wide temperature, 286 Kelvin. And that's in the middle of space where the temperature is 1 Kelvin or so, okay? So Earth gives off infrared radiation. And as it turns out, some molecules are really good at absorbing infrared radiation. The type of molecules that are good at absorbing infrared radiation possess a dipole moment, okay? And so this picture is showing you all of the things that happen to carbon dioxide when it starts to absorb infrared radiation. It makes the bonds vibrate, okay? And so if, let's say, my torso is the carbon and my arms are the oxygens, okay? It can undergo what's called the symmetric stretch, where each oxygen atom compresses and then recoils, and compresses and then recoils. Well, as it turns out, this doesn't give you a dipole moment, okay? Right? Carbon dioxide, if you look at this here, this dipole moment, the way that this thing is lined up, both of these cancel each other. So carbon dioxide does not have a dipole moment at rest. And when it's undergoing this symmetric stretch, it doesn't have a dipole moment either. So that's why it's called infrared inactive. However, if we look at what's called the asymmetric stretch, so this is now where one of these things moves in like this and the other moves like this. Okay, I'm watching myself trying to do this little dance here, right? And I should just pay attention to the screen. So this is called the asymmetric stretch. And as it turns out, there's definitely a dipole moment in that mode, okay? Right? When this oxygen is compressed, the dipole moment is very short on that side. And when this oxygen is elongated, the dipole moment is very long on that side. And that gives it an overall net dipole moment. In fact, it's a really strong overall net dipole moment, okay? There's also another infrared active, so that one's active. There's another infrared active mode, and that's called the bending mode. And that's where these oxygens are actually able to move up slightly like this and down, okay? And as it turns out, that also gives you a dipole moment because now in this configuration, I could draw the dipole moment pointing down this way, and I could draw the dipole moment pointing down this way. And overall now, or of course we could see in this configuration, it looks like this, right? And when it's in this position, there's an overall dipole moment pointing down. And when it's in this position, there's an overall dipole moment pointing up, okay? Well, how is it that that influences, or how is it that infrared energy can do that? Well, when we look at a wave of light, okay, so here's like a, let's say a couple waves of infrared. And let me draw a little dotted line through the center of that, okay? Well, as we discussed in chapter 7, light is an oscillating electromagnetic field. We talked about that very briefly, okay? So as light is going through this wave, there is actually a dipole moment created by light itself, okay? And so that's why I wanted to draw that dotted line right there, because you can see at each crest and trough, the dipole moment increases. And if we were to align a carbon dioxide molecule in this dipole moment, okay, like let's say I'll put one right here. So here's my carbon, and I'm just going to draw it, without the correct Lewis structure. I'll just draw it like that, okay? So now as this wave propagates through, this influences that bond to stretch. And then as it comes back down, it's going to influence it to compress the other way back until you get a full cycle. Hopefully you can kind of see that, right? So as that wave is propagating through the CO2, it's influencing it to go through those motions, okay? And what the carbon dioxide can do is absorb that excess energy. So it stores that energy in the form of these vibrations, okay? So the way that these molecules are vibrating is a way of storing that energy. And because normally that infrared energy would go back out to space if there were no greenhouse gases, then that leaves the planet warmer because those molecules are storing that excess energy that normally would make it back out to space, okay? So as it turns out, CO2 is an excellent greenhouse gas molecule. And in fact, we should be lucky to have a little bit of a greenhouse effect because the planet would be way too cold, okay? Without the greenhouse effect, the average planet-wide temperature would be roughly 250 Kelvin. With the greenhouse effect, the average planet-wide temperature is roughly 280 Kelvin. And so we're talking about the average planet-wide temperature, okay? So 250 Kelvin as an average planet-wide temperature would mean that we'd be a ball of ice, right? Water melts at 273 Kelvin. We would be an ice planet if we didn't have some amount of greenhouse effect. Okay, so we do want some, but right now we have too much. We're overwhelming our planet's ability to deal with that excess heat. Okay, so CO2, because it's polar, or it can induce a dipole moment from infrared energy, is a good greenhouse gas, excuse me. As it turns out, H2O is a really good greenhouse gas molecule. It has a bent geometry, and we didn't talk about this so much when we did the Lewis structure. I just kind of drew it flat. When we get into the next chapter, we'll see that water is actually bent. And so that means that it has a dipole moment at any configuration. So water is a great greenhouse gas. Another one, which maybe is kind of surprising because at first it looks symmetrical, methane is an excellent greenhouse gas. In fact, methane, mole for mole, is a much better greenhouse gas than is carbon dioxide. And when you look at this, you might think, well, methane at rest has no dipole moment, but it can undergo these asymmetric vibrations, okay, which allow it to interact and absorb infrared energy. And in fact, it's a much better greenhouse gas because for a given atom, right, carbon has 2 bonds, but carbon dioxide has 2 bonds, but methane has 4. That's 4 bonds that can store infrared energy in the form of these molecular vibrations. Okay? So, in fact, if we were to release a lot more methane, that would be devastating for the planet. So there's a lot of people that are pushing for more combustion of methane, which of course we know when you combust methane, it releases CO2, right? But any uncombusted methane, if you don't do complete combustion on that, that's also going to contribute to the greenhouse effect. So in general, we should not be burning fossil fuels at the rate that we are. That's the moral of the story. Even if someone tells you, oh, but methane is far more efficient. It is, but it's still a greenhouse gas, okay? And then really even the same with biofuel, okay? When you burn biodiesel, you're still burning hydrocarbon. You're still putting CO2 into the air, and you're still putting uncombusted fuel into the air. Okay? So that's really why we should just be moving away from fossil fuels completely. Whether it be methane or octane or coal, we should really just move away from them completely because of what's happening with this greenhouse effect. So I know I only described that very, very briefly. I would encourage you to read more, maybe watch more videos, read more in the book. There's obviously a ton of information out there, but I just wanted to touch on the basics of where the greenhouse effect starts. And it's all about the chemical bonds, which is pretty cool. Okay, folks, that's it for chapter 8. So our exam 3 covers 7 and 8.